Good morning, everyone. How's everybody doing this morning? So, I'd like to begin. So, since we're live streaming, my name is Alan Pisano. I'm the lead capstone senior design professor, and I'd like to welcome all of you here to our 2017 ECE Day. And I just want to begin by saying that the format will be that each team will make a presentation. We have 4 sessions grouped by topic. There will be lunch after session 2, and then after the 4th session, there will be a demo phase where all the teams will have their projects around the atrium and some of the side rooms on the 9th floor for everyone to come around and take a look at. So please do that. We do have a big group of students this year who've worked extremely hard for the last 2 semesters working on their projects. So much so that I've seen a bunch of students in the lab, and I've actually asked them, do you take any other courses here at Boston University? So I think that's a tribute to all of you. This is your day. And as I say, of the 25, we have 25 teams of students. Also this year we had 3 senior honors thesis students. And so this is the biggest class I think we've had. And I think you'll enjoy the day. The format will be each team will make a short presentation, and then I will open it up to questions. I will defer to the judges for questions, and if there's time left, I will open it up to the audience for questions. If you have a question that we don't have time for, you can always ask the student teams during the demo session. This time I'd like to at least introduce the distinguished panel of judges who will actually decide who is winning the awards today. So they are seated at the front table. So maybe you stand up as I announce your name. We'll start with Ryan Lagoy from BAE. Next to him is Zach Lister from MITRE. Tara Adams from Paytronics. Marissa Petersill from National Grid. George Matthews, who needs no introduction, from Microsoft. Sam Howes from Google. Peter Galvin from Charles River Analytics. Brad Ruffleth, who's from GE, who's been a judge here, I think, every year we've had alumni judges. So I think this is a tremendous commitment on his part. And then Mikhail Gurovich, who's an independent entrepreneur who came up from New York City. So we're very pleased to have them here today. So I think without further ado, let's begin with session 1. So session 1 team is E-Fire 2. I would ask that each team, whatever student is speaking, to speak into one of the microphones, okay, so that we can hear everyone on the live streaming video. So each session has been grouped according to topic. So we're going to begin session 1, advances in measurements and electrical platforms. The first team is Team 7, E-Fire 2.
You ready for the video?
Need some sound.
Is the sound working on here? Okay. Oh. There we go. You see, you guys can see that because it's on the big screen. Okay. You guys not doing it.
In a world before E-Fire, measuring electric fields required large experiment booms. Then, our professors had a vision.
Hello, we are E-Fire 2. I'm David, this is John, this is Alex, this is Dylan, and this is Sammy. And our customers are Professors Nepper, Walsh, and Fritz. So you might be wondering, what is E-Fire? E-Fire is electric field instrument using radiated electrons. Our objective is to create a system to measure electric fields. Our project is a proof of concept. So this is actually part of a larger project. Our specific contributions were creating a system to measure simulated electron energies. So for our input, we have simulated electron hits, and for our output, we have electron energies, which is the main parameter for being used to calculate electric fields. The future iteration of the system will be placing the hardware that we created in a CubeSat, where the input will be electrons from a radioactive source, and the output will be the electric field measurements. So the competing technology that you saw in the video is a double probe, and so it has very large booms that are over 100 meters, and it's not that great for measuring DC values of electric fields, and it's large, bulky, and costly. So a future iteration of the project, and for what we are working towards, is creating a system that would eventually be resized to fit into a CubeSat. So this will be smaller, modular, and cheaper. So a quick general overview of our system is that for inputs, we obviously power it up. We have the simulated electrons, and then out come the electron energies.
In order to go into a bit more depth, the main core of our system are the analog and digital boards, which serve as electrical connections for the main communicating components, the MyRock 2 chip and the FPGA. The MyRock 2 chip takes in the Gaussian voltage pulse inputs from the pulsar and charge terminator pair and converts them into an 8-bit serial ADC output. This output is then sent to the FPGA, which relays it through the Arduino to the GUI, and then for data collection.
So you heard John refer to MyRock 2, and I want to give a little bit of background on what that is because that's very important to our project. So MyRock 2 is a custom integrated circuit that takes voltage pulses as input from multiple detectors and then returns an 8-bit ADC conversion of those energies along with the ID of the detector that it came from as output. So MyRock 2 provides the core functionality of our project, and it's what allows us to input simulated electron energies and then to return that back out to the system. And a very main portion of our project was testing MyRock 2 because this is a proof of concept and we want to demonstrate what MyRock 2 can do. So we were able to demonstrate that multiple channels worked, and also we were able to demonstrate linearity of the input energies with respect to the output ADC values. So a large portion of this project was hardware design. So here you can see an output of the PCB layout as well as a physical picture of the PCB itself. So you can see the black square right here. That's the socket which contains MyRock. MyRock is an 88-pin chip, and we connected all 88 of the pins. And the pins serve three main functions. Some of them provide bias power to the chip because MyRock needs very specific bias values. It needs to be biased with plus 1.65 and minus 1.65 volts. Then there are also pins which serve to take inputs from our simulated electrons, and those are the SMA ports, which you can see 5 of here and 6 of down in that corner. And it also serves to communicate with the digital board, and from there the FPGA, the Arduino, and our GUI. And it does that through the 50-pin D sub, which you can see is on the right side of the board. And that sends both communication signals from, control signals from the FPGA, as well as sending data back to the FPGA.
So the next board is the digital board. So the digital board essentially acts as an interface between MyRock on the analog board and our FPGA. So it's mainly used for logical level shifting. So the FPGA has logical values of 0 and 3.3 volts, whereas MyRock has negative 1.65 volts and positive 1.65 volts, as Dylan said. So it's mostly used for that interface. So this way the FPGA can send control signals to clock MyRock and make sure that it's working properly, and so that MyRock can send the ADC values to be able to use to calculate the input energies.
As David said, the FPGA is the main control for the MyRock 2 chip. It listens to see if there's an electron hit, and then that electron hit will cause a trigger which starts the ADC, which starts the FPGA. The FPGA then sends the corresponding select bits for the channel and the ADC, and then sends the start signal. Once the start signal is sent, the conversion will begin, and then the clock signal will be sent. After 10 clock cycles, the conversion will be ready to be withdrawn by the FPGA. The FPGA withdraws the 8 serial ADC bits and then sends it to the GUI for data collection.
Once the GUI receives the data bits, it plots them into a time-based energy plot that shows which energy hits were received at which time, as well as another plot simultaneously which contains the distribution of the energies received. These data hits are collected into a CSV file which can be opened and viewed for later purposes.
So the future of this project is to actually use real electrons from a radioactive source, as it would be in the CubeSat. And so to switch from that, you need to know kind of the physics behind it, and that in space, when you have an electric field and a magnetic field in orbit, and you send an electron, it will actually travel in a circle. But it doesn't have to be a perfect circle if there's electric and magnetic fields aren't perfectly matched to each other. And so it'll create a displacement on a diode array, which we can then use to transfer to an electric field measurement based on how far it's being displaced. And to do that, you need a biasing board, which you can see on the left-hand side, which is the little thing that you see with the wires coming out of it is an actual diode array, which you can then use to find a change in R based on which array or which diode it hits on there. That thing you see there has 3 channels. And on the right-hand side, you can see a vacuum chamber, and a small little square with Kapton tape on the middle is a collimator, which will direct particles to hit certain diodes. And that's needed so that way when you move to the next step of the electric field measurements, you can say, if it has this displacement, this is what the electric field is, and you can actually test what results you get.
So what did we accomplish? We developed a system for testing MyRock 2. This includes fully functioning hardware to software communications, starting from MyRock 2 and ending at the GUI. So in conclusion, we created a proof of concept for measuring simulated electron energies. Hope we got you fired up.
Probably
About 200 to 300 kilo electron volts.
Just DC noise from our pulsar. You can borrow one of ours.
So the diode array works by reverse biasing the array, and you will. It works by reverse biasing. It works by reverse biasing this array, and so this array, the ones that we used were meant to hit actual electrons that were about 400 kilo electron volts to 1 MeV. And so this needed to be at around negative 230 volts. And so what happens is we just power it through a BNC, and then it goes down to here, and it creates basically a DC value. And when an electron hits this thing, it will cause the diode value, breakdown value of this to change, and that will cause a dip in the voltage that this input or this output of the diode sees, and that gets converted to the MyRock chip, which can then amplifies it and also shapes into a Gaussian pulse, which we were using basically as a pulsar. And so that's the overall operation of how you can get from this to a value on the MyRock chip.
And the measurement takes place because of the V cross V drift of the electron, and also the magnetic dipole gradient, I believe. And these cause very minor displacements of about 3 to 7 millimeters, which we can then use the detectors as discrete distances. And then with the energies, there are 3 equations and 2 variables, which can be then easily solved for, one of them being electric field.
We got close. We ran out of time at the end. Yes.
Power consumption of the whole system, or which part? It's about 400 milliamps times. It's like
We didn't
250
pay
milliamps.
too much attention to the power since we just wanted to create a proof of concept, and we wanted to know the system works as it is, and then we can further reduce it after that if we so wish.
Okay, our next team is team number 5, Aeronomy Radar.
Hi, we're the Aeronomy Radar team. I'm Sebastian, this is Jetchen, Rushin, and Vitusha. So, what is our project? Well, we have created a software-based radar system that is capable of detecting human and metal targets and determining how fast they are traveling. Why is this important? Well, our project is a proof of concept for a radar system that is meant to study the atmosphere, and its main benefit is that it is cheap. Because our radar is software-based, not hardware-based, we're able to develop a system for the fraction of the cost. Each radar node is only $300. This is because it is based around the Red Battaya board, a new board similar to the Raspberry Pi. However, it has an FPGA, DSP units, as well as a radio transmitter and receiver. So little external hardware is required beyond that, an antenna, some capacitors, resistors, just a simple passive filter. And this makes our system faster and easier to deploy. Our system, because we took a software-defined radio approach, it is easily modular, or it can change to any application that a radar system could do, simply by changing the waveform you want to transmit as well as the FPGA layout. So our final product came out to a radar system that we tested in a control environment to make sure it was stable, and making sure that we have identified the trade-offs in quality that came with developing a radar system this cheap. In the end, we were able to transmit and receive a 47 megahertz signal, process that signal, and detect targets. We have identified the trade-offs and documented this for a system this cheap, and hopefully other radio hobbyists and teams will use our system for their applications.
So this is a video of our system in action. So to start, this is system setup. So we have 2 wire antennas which are connected to the inputs of the Repetaya board, and also we have a passive filter connected to the input. And this is connected wirelessly to our PC, which has GNU Radio, which is our transmission software, and both are connected to each other via the router, via Ethernet. And we also have our data processing program on the main PC. So for data collection, you can see Rushin acting as a target, being detected by our radar system. So he's holding a piece of metal, and it's being picked up by the wire antennas. And from here, there's the received data file is processed with our program. So this is a time domain plot. We also plot a frequency domain plot, and we partition this into frequency bins. And the bins, this is the power spectrum plot. So this is how we calculate Doppler based off what the power in the bins are. So for a technical overview of our project, there's 4 main components. So the first is the transmission receiving of the signals. So we've created a CW radar, and we've also begun the steps of making an FMCW radar. And we use the software GNU Radio to transmit our waveforms, which you'll hear more about later. The second part of the project was the Repetaya hardware. So because the board was so cheap, and there was a lot of trade-offs in terms of stability of the radar system. So this was trying to optimize the board and making sure we could still get a clear waveform even though the board was cheap. And the third part of the program is the data processing. So loading our received waveform that our radar system picked up and processing it to detect a target and tell us how fast the target was moving. And the fourth part is trying to understand how we can translate our proof of concept into a product that could actually be used for ionospheric imaging, because that is ideally what our customer wants to use the product for.
And the software we are using is GNU Radio. It's a free open source software which helps us to configure the FPGA to transmit a signal on a specific frequency. And GNU Radio also functionizes the Repetaya as a CW and FMCW radar. And for the CW radar, we transmit a continuous wave and hear the echoes from targets. And based on the Doppler shift, we can get the velocity of the targets. And the FMCW radar can provide the distance of the targets. Like we shift the frequency of a stable, known, continuous wave up over a fixed time period, and mix the transmitted signal with the echoes from the targets to produce a bit signal, which provides us the distance of the target after demodulation.
Okay. The Repetaya used in our project is a Darren board, which can be used for spectrum analysis and oscilloscope. And in this project, we are going to use Repetaya directly connect to our antennas, so which needs us to optimize our Repetaya through impedance matching and cutting off the clipping signals. The first step for us to debug our radar is to show how clipping and how noisy our signal is. And so in this project we are using MATLAB to help us visualizing the signal and in both frequency and time domain. And from visualization, we found out that we need a high-pass filter to cut off the 60 hertz power signal, which copies our ADC, and also which is messes up our measurement. To solve the coupling problem, we need a high-pass filter with mainly 10 picofarads capacitors. Also, in the future, we need a transformer, hopefully a transformer, which will give perfect power efficient about 90% better than what we have now.
So the next part of our project is the data processing program. So basically taking our received signal and trying to figure out if there's a target, and if so, how fast it's generally moving. So the way we did that was with a Python script that loaded the received waveform and the sampling frequency, and we plotted this waveform in frequency and in time. And specifically in frequency, we didn't use the DFT. We actually had to use a subspace frequency estimation method algorithm, because the target frequency and the feed-through tone are so close that you wouldn't actually be able to distinguish the peaks, so we had to use a different algorithm. And based off this, we split our frequency domain plot into frequency bins, which we could use to identify the Doppler. And so specifically here is some of the plots generated by our program. So in the top image, you can see the frequency domain plot, and the dotted lines are the bins as they're partitioned, and the bottom plot is indication of like the power density of each bin, and the higher the power, that identifies the target, and from there, based off the bin frequencies, you can identify the speed.
Yeah, so since our product is a proof of concept, two major things have to happen before we can move on to it being a full ionospheric imaging radar. So one is converting from a CW to a pulse radar. We need GPS triggered signal transmission, and we're working with someone at Repeti, the company that makes the board, and they're developing firmware / FPGA code for that. We can just insert that into the project, or the customer can just insert that into the project once it's finished. We've also started using FMCW signals to try and obtain range, not just Doppler. And here's an example of that. It's not that important, but it can be done.
We have our customer installation this week, and here's the feedback. Okay, our project has two main pieces, the data collection and the data processing. And now we can detect moving targets and make a radio velocity estimates. And for our future plan, customer future plan, the first is eliminating the noise by adjusting impedance matching, and then inserting the FPGA code so that we can have the time synchronization between radar nodes. And last is just adding the background subtraction so that we can transmit the FMCW signal for the range detection.
So again, this project's a proof of concept, and we're able to prove that our board is stable enough to be used for this application. So thanks.
Thank you.
Questions. So what is the range that you get with this radar? How far away can you detect a moving object?
So it's about 5 meters, but that's because we're using wire antennas, so they're really inefficient. But say you replace those and increase the power of the transmit signal, you could go farther.
Okay, good. And did you look at the isolation between the antennas? Were you able to measure the direct coupling from one antenna to the other?
We just noticed it when we were looking at our signals, because you could see there was like clear clipping, but I think they were farther enough that that wasn't the main issue. It was really the power supply that we were really struggling with to eliminate.
Okay, cool. Thank you.
Thank you.
Okay, you guys ready?
Yeah.
Okay, our next team is team number 4, SpotCheck.
Hi everyone, so we're SpotCheck and we have a great product for you today. So at the beginning of the semester, Professor Unlu's lab developed a brand new microscope and it's label free. So we're trying to assay biological assays, and the problem is that there were no efficient ways to analyze these arrays of microspots. So these microspots are important because you can use them in tests of like antibodies to see if certain drugs work or not. So our solution is SpotCheck. So it's a user-friendly cross-platform desktop application used for the analysis of microspot images. And it's made for anybody who wants to analyze the quality of microspots. And it greatly improves the efficiency of microspot analysis. So our final product imports images and metadata of microspot arrays and automatically detects the spots and images. And then we can apply user-adjustable image metrics onto the spots. And then we can export the data into a CSV as well as visualize them inside of our application. So here's a video demo of the product in action. And let me hit play.
To start, users can easily import their image and metadata files into the application for analysis. Users simply click and drag to select the spots they wish to analyze, and the application will do the rest of the work. Users can adjust the thresholds of individual spots to ensure that they are found. By default, the application calculates area, average radius, volume, and circularity. However, users can implement their own metrics in JavaScript from within the application to be included in the analysis. Results are displayed in a table at the end of the analysis. Charts can be generated from the resulting data. Results can also be exported to Microsoft Excel for further use.
So just to talk a little bit more about the overall design of the application, SpotCheck is set up into 2 distinct different areas. There's the front end and the back end. I focus primarily on the front end. I worked on the project as a front end designer and developer. The front end encompasses everything that the user sees and interacts with. That's everything from analysis tools to just simple, button clicking to navigate throughout the different pages of the program. It was primarily written in JavaScript and HTML, and the majority of my work was done basically emphasizing a clean and very intuitive design to make sure that we can eliminate all sources of user confusion. And I think the final project reflects that quite well and is very easy to use.
So I'm Nevin, and I worked a lot on the back end. So I built off the custom framework that Evan built, and I implemented a lot of the metrics in the back end, as well as helped develop the framework for future extensibility. So if a user wants to add more metrics to measure their microspots, it'll be very easy to do so.
So I'm Daniel. I worked with Nevin on figuring out how to use OpenCV to figure out how to use their image processing functions to get the information that we want and implement how to create a number that accurately reflects the metrics that the user wanted.
I'm Evan. I worked on a lot of the project architecture, so setting up the project so that we can easily compile it for all the release targets that we support. I picked the libraries and dependencies that we used. We used Node WebKit as a platform for building the application. The backend is OpenCV, and it's implemented in C++. I did some of the work in spot segmentation, like picking the spots out of the actual images. And I embedded the script engine. I did some work in passing data between the backend and front end.
So early last month, on April 4th, the four of us met with Darren Savendler, who is a graduate student from Professor Unlu's lab, and we successfully installed the project onto his laptop. And the details of just actually obtaining the project, because of the way that it was built, is quite easy. You just can go straight to the GitHub release page, download the file, extract it all, and then just run the .exe, and it all works out just fine. So we did that with him, and everything was great. We went through a couple use cases of the project and decided that it met all of the project requirements as defined by our customer back in September. So we were very happy about successful installation. And just to wrap up, the final product, we're very happy with how it came out. It's very simple, very intuitive, very easy to use, but at the same time, it's a very powerful tool for researchers to get these analysis done on their spots much faster than what had previously been done. The product obviously has since been shipped to Professor Unlu's lab and also to a lab out in Germany, Cyanion Labs, who works closely with Professor Unlu's lab, so we're looking forward to hearing back from them with some feedback. The other thing is that Node WebKit that we used to develop and kind of wrap our project together was a great way to develop a modern desktop application and really made it possible for future development to be quite easy. If you want to implement new metrics, not only do you have options in the front end to implement something in JavaScript, but it's also very simple to just get the source code and write inside of one analysis file just another C++ function to implement another metric and have it work just by recompiling the code. So it was really great. Questions?
Yes.
So this has been going on for multiple years, the SpotCheck project. So what did they actually give you to start with? They gave you the microscope, and did they give you some of the software to run it, or
They gave us data.
they just gave you?
They gave us data to analyze.
Okay.
From the microscope.
So how do you get volume out of this data?
So the procedure works as follows. So we receive the image from the microscope. Then we pick out a square where a spot is. So the image is a height map, which basically expresses, okay, so you map from like a certain number of nanometers to a 0 to 128 pixel value. And then in order to find the volume, you just do a summation or like a discrete integration. So we basically add all the pixel values and then scale by the pixel value to height metric.
The pixels where the spot is, not all the pixels.
Yeah. So the relevant pixels. And part of figuring out what those pixels are is like segmenting it, doing like a Hoff transform or similar techniques to figure out what part of the spot if you want to measure. So if you want to check it out, you can come to our table later.
I will.
Yeah.
Thank you.
I was actually really intrigued by the customization you had in the measurement, like how you can change the metrics. Can you talk more about like how extensible is that?
To start, users can easily import their image and metadata files into the application.
Oh wow!
Right now.
Thank you.
So like this is what you.
Can we go back? It's fine. I can start talking about it. So the backend is responsible for loading the images themselves. That's done through OpenCV. We load the height map data in, and then we wrap the images themselves in JavaScript classes so that they're accessible from the front end. You can do this through the V8 API. V8 is the JavaScript engine. And then you can pass them to the user metrics as parameters. This gives the users access to all the pixel values. You don't have full access to OpenCV, but as long as you're doing something simple, it's pretty useful. Most of the metrics that come with the application are actually written in user scripts, so you can go in and see how they're implemented, write your own.
So what is the minimum height of the spot that you can detect with your OpenCV algorithm?
That depends on the input from the microscope. So we just assume that we get a 0 to 128 pixel value. There is a relevant thing, which is like background subtraction. So there's like the minimum background height of the image, which we usually try to average out because we want to see like how much a spot sticks above that. So we perform a background subtraction procedure just to get like the rise above the background surface.
It's really like, it's like the difference between the height of the spot and the height of the background. It has less to do with the actual height of what the actual units are. There just has to be sufficiently different. The height has to have a sufficient height that you can actually, like if you can't see it with your eyes, you probably won't be able to pick it up in the program.
But as for minimum height, that's a parameter of the microscope, which we're getting input from. Over there.
So what the lab currently, what the lab currently uses, they use ImageJ and they do it by hand. So you could take the hand done analysis and compare it to this. We haven't done that yet. Most of the metrics we implemented were like area, volume, circularity. They should work. It's simple enough that we're doing pretty basic math and it should work, but we haven't tested it.
I'm just going second, so I'll just have the second mic, I guess.
Yeah, we can just hand the second mic to whoever's going.
And then you're yeah, because it's the video.
Okay. The next team.
We don't have the presentation notes.
The next team in this session is team number 23, satellite tracking for LEO.
Thank you, Professor Pisano. So as you said, we're team 23, team LEO. This is Joe, Amber, I'm Kyle, this is Josh, and Zach. And we're team LEO, LEO standing for low Earth orbit, because the sort of motivation for our project, the problem that we're solving is that low Earth orbit satellites are difficult to communicate with. Primarily they use radio, which is very low speed and very high latency. So the method of fixing that is by using optical communication instead. But with optical communication, you need a direct line of sight between the transmitter and the receiver. And optical comms require a fast-moving receiver, and most telescope mounts move very slowly because they're meant to look at things much, much further away, and they have a keyhole at the top. So if something is passing right overhead, it's difficult to actually maintain a visual lock on it.
So basically the is this on? This is not.
I don't think it is.
All right. Oh, there we go. Wow. Okay. Okay. So basically, the crux of the problem is that there's a blind spot directly overhead, and essentially that is the most important spot where you need to be tracking these satellites. So part of our solution is actually translating this coordinate system. So traditional telescope mounts use an azimuth and elevation model, but we're using an altitude-altitude or alt-alt model, So this actually shifts the blind spots to the horizon. So instead of not having any information directly overhead, you instead don't have any information around the horizon, which is the least important area where you're tracking things. Our main goal was to build a prototype for research and development. So this was more or less a proof of concept that this sort of tracking could be done on a very low budget. Our customer also gave this project to a professional company who built a prototype for around $50,000. Conversely, our mount cost about $2,500. So we were able to achieve high precision and allow for control systems even with our lower budget. And we also have an integrated video feed to verify our results.
The Team Leo mount has two axes of rotation, a horizontal primary axis and a secondary axis, which rotates about the primary. Each axis is driven by a geared stepper motor and has an optical encoder for position feedback. The relation of the two axes allow for objects to be tracked in the sky rapidly and accurately without blind spots.
So just a little bit on the technical overview of our mount. Our mount features 2.018 degree geared stepper motors, 17-bit absolute rotary encoders, an imager with 640 by 480 resolution. Our telescope has a 4-degree field of view, and this all runs off of an Intel Minnow board running Windows 10. Our project also has an RTL SDR with 2 to 6 decibel higher gain than the previous model, a USB GPS unit, and OpenCV for visual tracking.
Hello, my name's Joe. I was involved with the mechanical and systems design and integration of the mount. So I started with taking the customer requirements, turning that into component specifications, and then selecting the off-the-shelf components that met these specifications were necessary. I then rolled those off-the-shelf components into the mechanical design of the mount, analyzed the design, and then led up manufacturing oversight. It was built in BU's EPIC machine shop. Once all the custom parts were done in EPIC, I led up the mechanical assembly and integration of the mount, and then finally installed all the electronics, did the electronics hardware integration, and all the wiring on the mount.
Hello again, I'm Kyle. So the idea was to make this a complete system. So we set this up on an embedded board called a Minnow board turbot. I was in charge of setting up the firmware and the OS for that. I also programmed the OpenCV visual tracking. As you can see there, that's just a one image shot of it. I programmed that in C++ to be easier on our little CPU. And then I did the motor control code in Python 2.7 with the Fidgets APIs, and then I integrated the software together with Amber's path prediction.
My name is Zach. I worked on the auxiliary systems for the mount. So one of the first things I did was build an antenna to capture ADS-B messages, which essentially is capturing position and velocity data from planes. So the primary application of our mount is to track satellites in low Earth orbit. However, our customer also expressed interest in tracking high-altitude balloons, which behave very similarly to planes. And integrating plane tracking also allows us to increase our testing cycles. So if we're able to go out and look at planes, you can do that during the day. There's very many of them. You can test significantly more frequently and debug. I wrote a software controller to interact with the antenna and the RTL SDR. So this essentially takes in the data that you see over here. It packages it into a nice data structure so that it's easily human readable. I wrote a linear time predictive algorithm for tracking these planes in real time. So the planes behave a little bit differently than satellites in LEO. Satellites in LEO, you have what's called a TLE, which Amber is going to talk about later, but essentially you know path information beforehand. With airplanes, there's no path information beforehand, so the tracking has to be done in real time. So I developed a linear time predictive algorithm that actually is suitable to be run in real time. And it does very well. It takes previous frames of plane data and then predicts the next 5 seconds. And then I also spec'd out and selected and integrated with a GPS module.
Hi, I'm Amber, and I was focused on the path prediction and coordinate transforms going on. So in order, one of the specifications from our customer was that we were supposed to take in a TLE, which is a 2-line element. What that is that has information on the satellite path. It doesn't give you velocity or anything like that, but it gives you information on like drag coefficients, when the satellite was put in orbit, and things like that. And from that TLE, you can run it through a program that has existed since like the 1950s, which is SGP4. And that just gives you, that takes all of the information in the TLE and that translates that into a position vector. And with that, in time, you can then get position, velocity, and acceleration. Those values are then what made our path and the path that the mount will follow. But the problem with that is those come out in values that our mount cannot understand, since we do have this new coordinate system. It's the altitude system, and then we added the tracking of stars and planets in addition so that it would have more capabilities.
Hi, I'm Joshua Klein. I did the GUI and software control system for this project. So our customer specifically said that our GUI needed to take in a TLE and GPS coordinates. So my goal was just to make a simple user interface that takes that data and then integrates that with the software control system, which binds together all of the software modules involved in our project and coordinates data transfer between them.
So as for customer installation, the mechanical complexity and precision of the mount actually forced us to modify the senior design schedule slightly to allow for more manufacturing time. So we are actually wrapping up our on-campus testing at the moment, and once we have finished that, we will hand off the mount to the customer. The mount comes with very simple plug-and-play capabilities, which the customer will be able to use to rapidly familiarize themselves with the operation of the mount and use those capabilities to build up their own purposes for R&D. In conclusion, the alt mount we built is a fully integrated system involving electrical, computer, and mechanical components all working together. It offers a very flexible research and development platform into alt mount technologies for use in tracking satellites as well as planes for increased testing flexibility. This will allow the customer to develop better mount technologies for use in optical communication systems on LEO satellites. We'd also like to take this opportunity to thank the ECE department for sponsoring what was a relatively expensive research and development project on our end. Thank you. Any questions?
Is it on now? There we go. You said that you were doing your testing now. Is it working?
So initially, yes, we are seeing some promising results. We have added onto the closed loop control of the mount using encoders the capability to also determine its position using a star field. The encoders require a calibration step that can be performed by the customer using equipment that is outside our budget, so that's why we added the star field capability. Initial testing, though, is positive that we are going to be able to hit the customer specifications for performance.
It looked like your resolution was kind of low. How did you identify and hold the track on whatever you ended up tracking?
So the tracking just uses very simple centroid tracking in OpenCV. Kyle can talk a little bit more about that. The resolution that we get off the imager will allow us to determine our angular precision absolutely to within 1.5 milliradians, which is higher than the customer specification of 1.3 milliradians, but that can be far exceeded using the rotary encoders that we have on the mount. So we can close the loop with more accuracy using those encoders.
Thank you.
Hi, good job so far. So two questions. So how does the user actually set up the object to be tracked? You mentioned GPS coordinates, but for airplanes, like, how do you do that?
In the GUI, we have a couple different options. There's the plane tracking option, and then there's the satellite tracking option. And when you do the satellite tracking option, the path is computed at the beginning using that TLE, and then it's matched with the time from the GPS. And once the satellite is overhead, it follows the satellite mechanically. And we just have the feedback through the camera in order to visually track it. And OpenCV will run on whatever the camera sees, which comes from my path and the control loop. Also, TLEs, those are available online. TLEs are kind of complicated in the way that satellite paths, especially in low Earth orbit, change a lot. So you have to have a TLE that's been relatively recent, like within the past 1 or 2 days. Things like the ISS or the Iridium satellites, all of those TLEs are available online. They're generally updated a couple times a week, so you can get it from that. And then when you're working with your own satellite, you have your own information more readily available.
So how long does it take to enter all the information and set it up?
The only thing that actually needs to be entered into the GUI is the TLE. It's 2 lines. The lines are a little bit annoying to enter, but once you have those 2 lines, all you do is enter it. Then the processing to do the path prediction takes like 2 seconds. It's very quick.
I'm wondering if you guys found any consequences to having your blind spot along the horizon. I guess I'm wondering why no one would have done that before.
So typically when you set up a tracking system for a satellite, you have redundant ground stations spread out all over the place. So if the satellite is going to be passing through the blind spot of one ground station, you're able to instead try to receive the signal from that satellite with a different ground station. A lot of that relies on the wider beam spread that you have with an RF communication system. With lasers, you have to be pretty direct with where you aim it. So you have to have your actual receiver stations very close to the actual track of the satellite to offer simpler aiming. And with that in mind, if your satellite goes over a receiver station or within that blind spot, you're unable to pick up the signal. So it's kind of a scenario forced by the change to optical communications compared to previous RF. It just wasn't necessary previously.
How do you do the original target acquisition?
This is a TLE question.
Are you asking about in the OpenCV program or in the...
So like when you set it up and you point it somewhere. How does the user know where to point it, and how do you know that you've pointed it at the right place?
Yeah, there's a 0, 0 that you point it to. So it points north, and the axis, the alpha axis is at 0. So you start at that point, and then the mount with the track will then go to the point where it has to. Beta axis will move, alpha will be at 0 because it'll be just going over the horizon, and then you just run the track from there.
Sir Swan, but I'll ask it anyway. You keep talking about the very nice piece of work, by the way. It's impressive. You keep talking about the blind spot, but I'm not sure what that means. Is it something in the sky, or is it an artifact of the mechanical structure? Can you just explain what the blind spot is?
Yeah, so it's an artifact of the mechanical structure of the mount. If you have an object traveling over the mount, there's a moment of increased acceleration as it tries to stay on that object. Basically, the axis that points towards that blind spot will have to rotate relatively fast, and that reduces your tracking accuracy. Any fast motions will lead to deviations from your intended path. So by shifting those blind spots to the horizon, your fast accelerations will happen near the horizon, which you generally can't see the satellite at anyway. There's too much atmosphere.
To do a very crude demonstration, it's like if you were tracking it like this and you get to the top, but then you have to spin and go back down. So at that point up top, when you're spinning on the, what would be the azimuth, then you miss the satellite at that point. Yeah.
while this next team is setting up, I just want to indicate that you'll see that the projects have a variety of customers. We have a variety of industrial customers. There are some alumni customers and faculty customers who've actually proposed the projects. The last team, of course, was MIT Lincoln Labs. This team coming up is Schlumberger, both of whom are industrial customers, and we're very grateful to the fact that they provided projects for this year's class. Okay, the next team is number 10. It's called NMR in a Coffee Cup.
Good morning, ladies and gentlemen, boys and girls of all ages. So I was told that if I came in today with my own coffee cup, I'd get 25 cents off at the door. Fortunately, I walked in with a coffee cup with something that fits entirely inside of it. Ladies and gentlemen, we are NMR in a coffee cup, and this is a culmination of our entire work's progress. I'm Arnab, this is Gene, Shen, Asad, and Nick. Our client is Schlumberger, an oilfield solutions company which provides technological innovations to petroleum companies and helps them become more efficient and come up with new ways they can drill oil efficiently and safely. So the problem is that NMR spectrometers are huge and mobile and are really expensive and are always found in labs. You cannot bring them to the oil site because you can't move them around. What Schlumberger wanted was something that fits inside a coffee cup, something small that you can carry in your hand and would conduct NMR NMR tests. What we have here is what this cup will do is basically save petroleum companies a lot of time, capital investment, and their employees' times from sending the fluids back and forth from the oil fields and to the labs. They can just conduct their tests at the sites. So what's inside of this is an NMR, a PCB, which conducts all the software, sends signals and pulses back and forth from the NMR, and the battery, which powers the device. Let's take a deeper look. So the NMR is basically a permanent magnet, which has a capillary tube inside of it, which has a coil around of it. The coil sends the electric pulses, the electromagnetic pulses, and the capillary tube is what holds the fluid inside of it. On the PCBs, we have an ASIC chip, which generates the frequency pulses, and the microprocessor is what sends the pulses to the coil, and then processes that data and sends it to the computer. And of course, we have a battery which powers the device. And now I'm going to show you a quick video which shows you how it works.
What you're looking at right now is a typical lab NMR spectroscope. As you can see, they're huge, expensive, and not portable at all. The objective of the NMR spectroscope in a coffee cup project is to shrink this technology into a robust, easy-to-use, and portable-sized NMR tool for field engineers and scientists to be able to test oil samples quickly, conveniently, and accurately while still on site.
So this program just basically tells the microprocessor to send the pulse. As you can see, we have a signal over here. What the signal basically is two phases with a 90-degree offset. There's an in phase and out of phase. What you see right over here, if you could come in closer, right over here where the yellow line does a break, that is where we send the pulses. You can see it's a very, very short amount of time. It's about 15 microseconds? 0.5, yeah. And that's where the signal comes, and then the signal's turned off. You can see that this is the relaxation time, the amount of time that it takes the device to come back to a constant. And this is what we would measure to be able to tell what the liquid, what the fluid is.
A coffee cup is not just an allegory for the size of this device. The final product will actually be housed in a real coffee mug. This is a drastic reduction in size from a full-size NMR, which is about the size of a car. We are very excited about our project, and we hope that you enjoyed this video.
Now I'm going to hand it over to Nick.
So our design for the circuit boards inside of this device kind of went through a lot of iterations. Our initial thought
when we were constrained by different parameters, was to have 3 rectangular PCBs arranged in a triangle fashion. As you can see right here, our idea was to put the magnet in the middle. From the very beginning, our biggest constraint was size. This is a very, very small device, and packing so much into it was always a challenge. So this design would have allowed us to fit the magnet inside of the PCBs and save on space there. It turns out that later on we were reconstrained to a smaller coffee cup, which we were very happy about. So we changed our design instead to 3 circular PCBs, as you can see, which we have today. Basically, the breakdown of the PCBs is we have power and voltage level generations on the first board. It also handles communications. The second board handles our microcontroller and all of its support hardware. And the third board actually does spectroscopy. It's got an ASIC designed by Schlumberger.
Yep. I want to talk about we came a long ways designing the cup. So what I'm holding in hand right now is what I have, final versions. So I want to talk about roughly we have 3 boards in our final versions, board 1, board 2, and board 3. So board 1 is mainly for power supplies. We have multiple of different voltage that's needed for all components for the whole boards. We have 3.3 volts for analog and digital. We have 1.8 volts for analog and digitals. We have plus and minus 5 volts, plus and minus 15 volts, and a reference 2.5 volts just for our microprocessor. To save space, I also put my driving signals to enable the coil circular duplexes in the board 1. In board 2, of course, we'll have big microcontrollers in there. We have our 8 transceivers that transferred the instructions that was outputted out of the microcontrollers, transform into acceptable ASIC chip inputs that's located in the third board. We also put a temperature sensor on the second boards, as well as a logic circuits for enabling the detecting coil circuitry duplexer. Third board is where all the analog receiving and transmitting is going on. There's an ASIC chips that generates the correct pulses in the more frequencies for detections. The connectors that connect all the coils for the MMR detections is there, and then as well as a face-off loop for our clock reference.
As you can see from the images, we have designed an internal housing that will fit into the cup. As you can see, there are 3 slots in the top where the 3 PCBs will be placed, an area in the middle where the magnet will be, and a compartment at the bottom where the battery will be placed.
When you have an important customer and you're working on this project, first you have to make sure that you follow the steps and model the final product before designing the real product. So that's what we did. We have to design the jigs, which go right inside the magnet, which was provided by the customer, and we have to model the cup to make sure that we really have the real idea of what we want to do with the real cup. Because the real cup isn't steel, we couldn't work on with it straight. So we did the modeling, and that's what we gave.
So how we're powering the device is using a lithium polymer battery. We picked this specific one because its size, it fits perfectly on the bottom of the cup, especially with the diameter, and it has watts 7.6, and the perfect thing about it was it fell exactly within the constraints of each of the PCB voltage requirements. Something else that we're really proud of is that Nick and I worked with Shen to create a micro USB input which would enable the device to be plugged into any laptop or say an iPhone charger in the power socket and be powered by that, as well as a rechargeable battery. So there's 2 different ways that we can power this device now.
So customer installation, we have been working very closely with the senior engineers in Schlumberger. We actually hand solder every single components in here. It's been tested, read by voltage meter. Every single reading is accurate, and we actually cleaned the board up for the presentation today. And then the second board 3 is coming very shortly. When it comes attached, we're gonna have a correct MMR signal detecting.
So here we are at the end. Basically, what went well is we're really proud of the way we managed to fit everything that Schlumberger had in 3 very small boards, and the fact that the device can be powered by both remotely and by a laptop source. if a future team was going to work on this, we'd just say that if they could enable Bluetooth functionality or a small screen on the device that actually shows what's going on in there, as opposed to right now we have it connected to an oscilloscope. So at the end, we'd just like to give special thanks to David McCowan, a senior electrical engineer at Schlumberger, who's helped us tremendously, our client, Raytang, of course to the ECE senior design squad, the professors, and all the GTAs that helped us throughout and helped us create an amazing device. So thank you. Any questions?
So, if the original product is the size of a car, why the constraint to a coffee cup?
So generally, NMRs are the size that they are because they house enormous magnets. We're talking like tens of Teslas, right, in that range. They're usually cooled by liquid helium. One of the constraints we had was that we were going to use a very small magnet. They actually picked our magnet for us. It's about half a Tesla. So with that, we sacrifice a little bit of our sensitivity, but we can obviously fit in a much smaller package. So it has a very specific use in that sense.
So, you said that they constrained you to a smaller coffee cup sort of halfway through.
Right. The current coffee cup is 3.2 inches in diameter.
So I'm asking why such a small package instead of like a suitcase, because that's a huge improvement from a car.
So initially, so when we did ask them that, he basically, our client just wanted to push us to our limits. He wanted to be as small as possible. And we initially started with actually a 5-inch coffee cup, which that's why we went through so many iterations. And then finally, in around January or December, he said he bought that cup, and he was like, I want it to fit in here. And you got to follow the boss.
Two questions. How many users of one charge can you get out of it, or how many hours? And can you talk about the testing data? How accurate is it versus the original design?
Okay, I'll answer the first question first. So we did a few calculations and found that given the space that we have, given what the device demands, we can get up to about 60 hours continuous usage. We ran a lot of stress tests. It's a device which it's not going to be on completely. As you know, it's short pulses, so that helps us get a lot more hours in there. And sorry, could you repeat your second question, please?
Second question is, how accurate is it versus what they have, versus the big prototype?
So,
In other words, is it realistically placed in the field?
So we still have to yet to go to Schlumberger and test it. We've still got the second and third board coming in. That's coming in later on this week. And if you're around, hopefully I'd like to answer that later on. I'm sorry, I can't answer that right now. Thank you.
Did you have any intermediate tests to make sure that everything was working?
Yeah, so as any capstone project happens, we have constant tests throughout. We've tested each of the components throughout the semester, the battery stress testing of the supports, and we've recently been testing this board, and as Shen said earlier, it works perfectly fine, and we hope that when the second and third boards arrive in a couple of days, we'll be able to test that too. And if all the components are sold correctly, we know from our design schematics that should work for sure.
Okay, and one more. Does your coffee mug stick to refrigerators? Because of the magnet.
That would be an interesting idea. Why do you ask that?
Well, because of the magnet. Does it start to attract all these metallic objects?
It does have a very large half Tesla magnet in there, but the answer is no because it's actually shielded.
It's a shimmering magnet.
It's got half the magnet, and if we go back to the picture of it really quickly, do we have that up?
Yeah. The jig slide.
Right there. So you can kind of see there's an outer and inner component of the magnet. The half Tesla magnet is actually the inner part. The outside is just shielding for our electronics and also to stop interference from interfering with our sample because there's high frequency pulses going into and out of there. So no, actually that magnet doesn't stick to anything.
Luckily we got provided this magnet by Schlumberger, and it's about a $500 magnet, so it does its job really well.
So I'll answer your second question first. The entire device pulls about 2 or 3 watts continuously. So heating has never really been an issue for us. It is not a very high-power device. To answer your first question. Right. So first off, I'd like to say you don't have to worry about not being an engineer. We're not engineers yet either. Give us a couple of days. But the reason why this is actually ABS plastic, and I talked to my customer, and he said, if we use the right kind of materials and enclose it around the magnet, then in addition to the shimmering magnet's outer layer, it should completely nullify the magnet's magnetic personality.
Okay, our last team for this session is team number 9, Vulcan Microfluidics.
Hello, everybody. I'm Shane McCormick. This is Alexander Nero, Julian Trin, and Anisha Stana, and we're Project Vulcan of Douglas Densmore's Cider Lab. So Vulcan aims to extend Cider Lab's biological microfluidics. But first, what are microfluidics? In short, microfluidics are manipulating micron or micro-scale amounts of liquid. And in terms of biology, this is using these manipulations to replicate biological phenomena, experiments, processes. Unfortunately, microfluidics in biology is a pretty niche market. There's limited functionality and very, very high costs of entry in terms of cost, time, and expertise. So Project Vulcan aims to basically simplify and extend both the design of microfluidics and the biological capabilities of the Cider Lab microfluidics at low cost.
And this is Vulcan in a nutshell. Our project features a Verilog-like hardware description language called LFR, which users can use to define their microfluidic components, which then gets compiled into a blueprint, which then you can feed to a CNC machine to actually mill out a chip. We have hardware modules that can interact with the chip by replicating biological experimental processes such as PCR by heating and cooling the chip, as well as an observation module that can look at the liquid and extract experimental properties out of it. The interface between these modules and the user is something called the peripheral manager, which handles all inter and intra-module I/O between the modules and with the user. So what this allows users to do is just enter in experimental parameters, hit run, and they'll be automatically executed through the modules. And we have our demonstration video next.
Welcome to Project Vulcan. To create a microfluidic chip, the user specifies its structure in LFR. Then, LFR gets translated and turned into a physical blueprint. We can take this blueprint to a CNC machine and have the chip milled out. With a PCR-compatible chip, nichrome wire and temperature sensors are connected to conduct thermal cycles. On the left, we can see that the temperature-sensitive dye is going in purple and coming out warmer in pink. With a characterization-compatible chip, a USB microscope is used to capture video data and analyze droplets. We can see on the right that they're being identified and characterized as they pass. The Peripheral Manager allows users to control multiple modules and view module output data from microfluidic experiments. Here, we give the PCR module a set of parameters, and we can view the thermal output in real time.
And now with LFR, Shane.
All right, so I mentioned barriers of entry earlier. Designing microfluidics is definitely one of them. Contemporary microfluidic design is very difficult, tedious, and most importantly, manual. Basically, microfluidic designers have to draw up their designs by hand, and if anything needs to be changed, there needs to be redrawing. So with that in mind, I've been developing a more simple design language for microfluidic creation. Users can use simple Verilog-like assigned statements to define their microfluidic chip in terms of parametric components. And then once they've done this in my LFR design standard, I then translate and output their microfluidic chip in CIDR-compatible code, and then that can be CNC milled from the blueprint you saw in the video.
So the Peripheral Manager provides an easy-to-use interface for controlling and managing any hardware modules you have connected to your computer. It allows users to send and receive data from the modules, visualize this data, define connections between modules so that they can communicate with one another through the Peripheral Manager. There's no direct connections between them, as well as log all experimental data so you can analyze this stuff in the future. It also allows users to import like predefined custom experimental schedules so that you just import a JSON file and get started immediately without having to enter any information.
So the goal of the PCR module is to heat and cool fluid in a microfluidic chip to induce some biological reaction, namely the polymerase chain reaction, or PCR, which clones and replicates DNA, for which it is named. So to achieve this, I created a circuit connected to nichrome wire that goes through a PCR-compatible chip. This is connected to an Arduino, and with the PID controller, the Arduino can control the temperature. The Arduino receives temperature input from two thermocouples on either side of the chip, and using a mathematical model that using mathematical model that kind of graphs out the heat transfer in the chip, it can then predict the temperature of the fluid. And then using this temperature, it varies the power in the nichrome wire to either heat up or stop heating the chip. In order to achieve the desired temperature, it then can maintain that temperature for any time that the user states. So our end result is a reliable controller with a good steady state error and RAM times that can compete with PCR machines in the market today.
So previously, there really wasn't a fantastic way of gathering data from microfluidic experiments. So we decided to design a portable Raspberry Pi-backed computer vision module that can take live video data as well as video files to characterize, track, and identify individual droplets as they move through the channel, as you can see there. For live experimentation, we had a USB microscope that hooked directly into the Pi that fed live video data, and we were able to extract properties of the droplets such as size, color, rate, and speed, among other things. One of the best parts about this module and Vulcan in general is you can set up your experiment, enter in your experimental parameters, hit run, do something else, come back, and you'll know that you'll have a log of output data to analyze later.
So we've been integrating with CIDR Labs since day one to make sure whatever we build matches whatever they need for their experimentation. As such, most of our customer installation period was spent stress testing LFR, droplet characterization, PCR, and the Peripheral Manager. Another thing we worked on during April was integrating with a tool that the collaborators at Northern Arizona University built to, again, allow users to easily schedule experiments and just importing that. We also uploaded all of our code on GitHub, so again, it's open source. Anyone can see it. Anyone can define their own modules and extend on this project.
So Project Vulcan has successfully advanced the field of microfluidics through adding functionality to conduct experiments. We have also created a standard for these modules that anyone can then add their own modules into this expanding library. So for the future of Vulcan, Project Vulcan will be involved in various CytoLab microfluidic experiments, as well as the current software Neptune and the iGEM competition of BU that they compete in every year. We will also be presenting Project Vulcan and the LFR changes to IWBDA, the International Workshop of Biodesign and Automation, this summer. And finally, we have outreach with other labs in the area where we will be adding functionality to their microfluidic experiments. We just want to thank our customer, Professor Douglas Densmore, our CytoLab, including our graduate mentors, Ali and Krishna, and we want to thank our professors and our GTAs for the ECE Senior Design course.
What are some of the parameters that you have to input when you're getting started?
So for creating the microfluidic chip, there are those assign statements, as well as basically almost parameters. Like I call it a user constraint file, UCF. And in there are a library of parts in which basically with a change of a single number, whatever parameters on that component that you've edited can be completely changed. And that's kind of getting around that having to redraw everything. You just change a number and rerun, and you're all good to go. Yeah, in terms of the experimental inputs, you'd be inputting, for instance, the temperatures you want to cycle between in PCR, or something along these lines. Sure. So basically, the goal of microfluidics and biology is basically, for instance, you're trying to test a gene, the expression levels of a certain gene, and you need to test many in levels of concentration of inducer on this gene. To see how well it'll express afterwards, say like glow green or whatnot with some fluorescent protein. So instead of running many experiments manually and pipetting things around, basically you design a bunch of chips and run them all in parallel to kind of automate and parallelize these experiments. So that's just one example in kind of what we're trying to do with microfluidics.
Yeah, so the microfluidic chips that have been fabricated at low cost in the CytoLab haven't really had like functionality built into the chips. So we added actual functional items to the chip other than moving liquids through, so we can